So what is screening effect actually? The inner electrons is screening or acting as a screen which keeps the nucleus away from the outermost electrons. So one electron is lost means the electrostatic force of attraction between the nucleus and the outermost electron will increase, right? One electron is lost, so the attraction will increase and the size will decrease. Now second ionization enthalpy means from Cr plus I am going to convert it into Cr2 plus. One more electron I have to remove. That means from the stable electronic configuration I have to remove one more electron. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 2 of the chapter DNF block elements. So in the last session, we studied about what is DNF block elements, right? Where it is positioned in the modern periodic table, right? As well as the transition series. What is the difference between transition series as well as D block elements, right? And then the general electronic configuration of DNF block elements, right? As well as the characteristics of transition elements, right? So in today's session, we are going to study about the general characteristics of transition elements. In detail, we are going to study about atomic radii, ionic radii as well as density, and how it is going to vary across a period as well as in down the group, okay? As well as the trends in physical properties we are going to discuss, metallic character as well as ionization enthalpy. So you're already familiar with all these concepts, what is atomic radii, ionic radii, ionization enthalpy, all that. So in D block elements, how it is going to vary across the period, group, and some extra features also we are going to study. Okay, so let's begin with the first one, that is atomic radii. Right, so the atomic radii of elements of a given series decrease with increase in atomic number, but this decrease becomes small after midway. So what happens here? We already know that as the atomic number increases, that means let's take the first transition series, that is the 3D series. I'm going to write here: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So this is the first transition series. So in this, we already know that as we move from left to right along a period or across a period, what happens? The atomic number is of course increasing, right? So as the atomic number is increasing, what happens? The nuclear charge increases, right? And the attraction, in electrostatic attraction between the nucleus and the electrons will increase. So what happens generally when we move from left to right? What happens as the attraction increases, the size of the atom decreases or the atomic radii will decrease. So this is how it's supposed to happen. But here what happens is, in the beginning, it happens in the same way. That is, towards the beginning, what happens is, as we move from left to right, the atomic radii will decrease. But midway, what happens is, in the middle, what happens is, the size will remain constant, or the atomic radii will remain a constant. It will neither increase or increase. It will be almost the same. But towards the end, after nickel, towards the end, what happens is, again the size will start increasing. Okay, so it will decrease, then it will remain a constant, and then it will start increasing. So why this is happening, or why there is a difference in the trend here? So let's see, in the first transition series, the atomic radius generally decrease from scandium to chromium. Till here it will decrease. Then manganese, iron, cobalt, all of that will have the almost same atomic radii, and from nickel it will again start increasing. So let's see what is the reason behind this. In the beginning of the series, the screening effect of a d electron is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases, hence atomic radius decreases. So what does this mean? Let's consider the different shells here. In the center you have the nucleus, right? Okay, so what happens here is, in the D block elements, we are going to consider the first ones, right? That is scandium, titanium, vanadium, all of that will have only few number of d electrons. So what happens in the beginning, the screening effect of the d electrons will be very less, because there are only few d electrons, right, which is present in the inner shell, right? For example, let's write the electronic configuration of scandium. It is argon 3d1 4s2, right? Only one d electron is present. So that is present in the inner shell and you have 2 electrons in the outermost shell, right? So what happens here? The inner electrons will have only very less screening effect. As there are only few d electrons, the screening effect or the shielding effect of the d electrons will be very less. So what happens? The inner electrons are not able to shield the outer electrons from the nucleus. Right. So what happens as the screening effect is less, still the electrostatic force of attraction between the nucleus and the outermost electrons still will be high. So what happens? They will attract each other and the size will become less because the screening effect is less. So what is screening effect actually? The inner electrons is screening or acting as a screen which keeps the nucleus away from the outermost electrons. So what happens when this inner electrons are not able to screen the outer electrons? What happens? Still the attraction will be more and the size will become less, or the atomic radii will become less. So this happens in the beginning. Now what happens? In the middle of the series, increase in nuclear charge and increasing in screening effect balance each other. So atomic radii becomes almost a constant. So what happens? Midway. Right. After chromium, what happens is manganese, iron, cobalt almost have the similar atomic radii. Now, why this is happening is because, yes, more d electrons will be present now. Right. More d electrons will be there. So, what happens? Screening effect is increasing. So, now these electrons which is present in the inner shell is able to screen or act as a shield between the nucleus and the outermost electrons. So screening effect has increased as well as the atomic number is increasing, means nuclear charge is also increasing, right? So screening effect is also increasing. Yes, so when the screening effect is increasing, the size should become more, right? Atomic radii should be becoming more. When the nuclear charge is increasing, what happens? The attraction should increase and the size should become less. Both of this is happening and it will be almost equal. Hence, what happens? It should increase as well as decrease. So, it will remain a constant middle way. Now, towards the end, let's see. Increase in atomic radii towards the end is due to the electron-electron repulsions causes the expansion of the electron cloud. Now, what happens? Towards the end, right? More d electrons will be present, right? So more d electrons will be present means what? The screening effect will be very high, right? So these inner electrons will screen the outer electrons from the nucleus. So what happens? The electrostatic force of attraction between the nucleus and the electrons will become less and hence the size will increase. So I hope this is clear. So in the beginning, what happens to the atomic radii? It will decrease. Why? Because the screening effect is less in the beginning, right? Screening effect will be less. Now, midway what happens? The screening effect as well as the nuclear charge will balance each other. So, what happens? There will be no change in atomic radii. And later towards the end, what happens? The screening effect will become very high because more number of d electrons, right? So, the screening effect will be more and what happens? The size will become more or the atomic radii will become more, right? So, as you can see, in the graph also, this is scandium, titanium, vanadium, chromium. So till here you can see a decrease in the atomic radii. Why? Because again I am going to say it is because of the screening effect is less, right? And here you can see manganese, iron, cobalt, nickel, all of them are having almost the same size or almost the same atomic radii. It is because the screening effect and the nuclear charge is balancing, right? Now after nickel, what happened? Copper and zinc, again you can see a increase in the atomic radii. Now, why is that? Because the screening effect has become more. Okay. So, I hope the trend in atomic radii is clear for you along a period. Now, we are going to discuss it down a group. Okay. So, let's see. The atomic radii increases while going down in each group. As we move down the group, what happens? We already know this. As we move down the group, yes, new shells will be introduced, right? So, as we move down a group, what happens? New shells will be introduced. So, new shell is introduced means, of course, the size of the atom will increase. That means atomic radii will increase, right? Okay, let's see. However, in the third transition series from hafnium and onwards, the elements have atomic radii nearly equal to those of the second transition elements. Okay, so the reason is this is due to the introduction of an additional shell at each new element down the group. Nearly equal radii of a second and third transition series elements is due to a special effect which is called as lanthanoid contraction. So that means that you have the 3D series, right? You have the 4D series as well as you have the 5D series. So what does this sentence mean? That yes, as we move down the group, what is supposed to happen? The atomic radii should increase because new shells are introduced. So what happens here is when we are moving from 3D to 4D series down the group, what happens is, of course, the size will increase. But when you are moving from 4D to 5D, when you are moving from 4D to 5D series down the group, what happens is the size won't change much. Okay, the atomic radii will be almost the equal. That is because of a special effect which is called as lanthanoid contraction. Right, lanthanoid contraction. So because of that, the 4D as well as 5D series will almost have the similar atomic radii. So I hope that is clear. So as you can see here, zirconium and hafnium. Zirconium is a 4D element and hafnium is a 5D element. Right, 5D series element. So what happens? 160 picometer and 159 picometer. You can see it is almost having the same atomic radii, and those goes with all the other examples also. So I hope that is clear, and this is very important. Why is that the 4D and 5D series are having almost the same atomic radii? It's because of this effect which is called as lanthanoid contraction. So I hope it is clear. Now moving on to the next one, that is ionic radii. So we just discussed about atomic radii. The same goes with ionic radii as well, right? Okay, so what is the difference there? Ionic radii is the radius of the ions, right? Okay, let's see. The ionic radii follow the same trend as the atomic radii. For the same oxidation state, the ionic radii generally decrease as the atomic number increases in a particular transition series. So generally, what is the trend here? As the atomic number increases, the ionic radii will decrease, right? Okay. For the same element, the ionic radii decrease with increase of charge on the ion. So now coming on to the charge, which is important, let's take Fe2 plus and Fe3 plus. So when Fe2 plus is getting converted into Fe3 plus, what is actually happening here? How that charge is getting converted? Fe2 plus to 3 plus means what? Yes, one electron is being removed, right? One electron is being removed from this. That is how it is becoming Fe2 plus to Fe3 plus. What is happening? The charge is increasing, but one electron is lost. So one electron is lost means the electrostatic force of attraction between the nucleus and the outermost electron will increase, right? One electron is lost. So the attraction will increase and the size will decrease. So when you compare Fe2 plus and Fe3 plus, Fe2 plus will have more ionic radius than Fe3 plus. So when the charge increases, what happens to the atomic radii? It will decrease, right? So I hope it is clear. Same goes with Ni2 plus and nickel 2 plus and nickel 3 plus. Who will have the more ionic radii? It will be nickel 2 plus, right? 72 picometer and 62 picometer. You can see here, right? So what is the reason behind this? Again, as one electron is lost, what happens? The attraction between the nucleus and the electrons will increase and the ionic radii will also decrease. So same goes with manganese 2 plus and manganese 3 plus. So I hope all these examples are clear for you. Now, moving on to the third one, that is density. All metals have high density. Yes, D block elements are metal, so they are having high density. Within a period, the densities vary inversely with atomic radii. So what did we discuss now? When the atomic number is increasing, atomic radii will decrease. And when the atomic radii is decreasing, the density should increase. So it is inversely proportional. When the atomic radii is decreasing, the density must increase, right? So densities increase along a period, right? So hence what happens? Just now we discussed when we move from left to right along a period, the atomic radii should decrease, right? Because of that, the density will increase. Now, also densities increase upon descending down the group. Now, the atomic values of transition elements are low because electrons are added in n-1 d subshell and not the ns subshell. It is the electrons are being added in the inner shell, not the outer shell, right? Outermost electron or the outermost shell is the ns subshell, but the electrons are added in the inner subshell, right? That is the d subshell, n-1 d subshell. That is why the density is becoming more. Therefore, increased nuclear charge is partly screened by the d electrons and outer electrons are strongly attracted by the nucleus. The shielding effect of this inner d electrons will be less. So what happens? The attraction will be more. And when when the attraction is more, what happens? The atomic radii, again it will decrease. So when the atomic radii is decreasing, what happens to the density? It will increase, right? So what happens? Consequently, the densities of transition metals are generally high. Okay, so I hope it is clear. Now moving on to the trends and properties of transition metals of first series, right? So first one, we are going to discuss metallic character. So we already know that D block elements are metals, right? So of course it will have all those properties which, so generally it will have all the properties which are shown by metals, right? So all the transition elements of first row are metals. They exhibit typical metallic properties like metallic luster, right? High density, high melting and boiling points, malleability, ductility, tensile strength, hardness, brittleness, all of those properties which are shown by metals, the D block elements, the first row, first transition series also will show, right? Yes, and they exhibit all three types of structures, that is cubic closed packed structure, CCP, or FCC, faced centered cubic, as well as HCP, hexagonal closed pack, and body centered cubic, BCC. All these types of structures they will show. Right, now moving on to the next one, that is ionization enthalpy. So you're already familiar with what is ionization enthalpy. Ionization enthalpy is the enthalpy which is required to remove one electron from the outermost shell of an atom, right, to convert it into a cation. When one electron is lost, what happens? It is getting converted into an cation, right? So how much energy or how much enthalpy is required for this process is called as ionization enthalpy. So now we are going to see across a period and down the group how the ionization enthalpy varies. Okay, so let's see. The ionization enthalpy increases in the series as the atomic number increases. However, the increase is not regular. Why this increase is not regular? Just now we studied the trend in atomic radii. The trend in atomic radii is also not regular. So atomic radii and ionization enthalpy is interlinked, right? So when the radii is less, atomic radii is less, ionization enthalpy will be more. So as the trend in atomic radii is not regular, the trend in ionization enthalpy will also not be regular. This is because of the effect of increasing nuclear charge is somewhat neutralized by the shielding effect. We have already discussed this. In a period, the ionization enthalpy increases from left to right. For example, ionization enthalpy values of scandium, titanium, vanadium and chromium are fairly close to one another. Similarly, the values of iron, cobalt, nickel are same and almost similar, right? Why? Because their atomic radii are almost similar. So let's see here the first and second ionization enthalpy of 3D series elements. So what is first of all first and second ionization enthalpy? First ionization enthalpy means it is the enthalpy which is required to remove the first electron from the outermost shell, right? And second ionization enthalpy is once it is getting converted into a cation, how much enthalpy is required to remove the second electron. That means, for example, let's take the example of zinc. Okay, so first ionization enthalpy means it is the enthalpy required to convert zinc to zinc plus, right? That is one electron is lost. Now what is second ionization enthalpy? Now from zinc plus, okay, plus charge, we are going to remove one more electron and form Zn2 plus ion. Okay, so this enthalpy which is required to convert Zn plus to Zn2 plus, that is called as the second ionization enthalpy. So I hope that is clear. So as you can see here in this table, the first ionization enthalpy is always lesser than the second ionization enthalpy. Generally, as you can see, it is 631, 1235, 656, 1309, and in all the elements you can see this trend. Generally, the first ionization enthalpy will be less than the second ionization enthalpy. So now we are going to see in detail for each of the element how this is happening. The value of the first ionization enthalpy of chromium is lower than expected. This is because the removal of one electron produces extra stable D5 configuration. So let's see what does that mean. For chromium, the atomic number is 24. That is, electronic configuration is argon 3D5 4s1. Right, it is 3D5 4s1. Chromium and copper are having exceptional electronic configuration. So coming back to chromium, it is argon 3D5 4s1. Okay, so what does the sentence say? The ionization enthalpy, the first ionization enthalpy of chromium is lesser than what it is actually expected. Now why is this? Because yes, in the outermost shell you can see there is only one electron. So if this one electron is lost, chromium is going to attain a half-filled electronic configuration. It is 3d5, right? Yes, d subshell can accommodate a total of 10 electrons. So d5 means, yes, that is half-filled electronic configuration. So if chromium is ready to lose that one electron, it is going to get a stable configuration. So chromium is ready to do that, right? So it is going to easily lose one electron. Hence, the ionization enthalpy is lesser than what is required or lesser than what is expected, because once this electron is lost, it is going to get a half-filled electronic configuration. So I hope that is clear, right? Now, the value of zinc is appreciably higher due to the additional stability associated with the completely filled 3D level. Okay, coming to zinc, what is the electronic configuration? It is argon 3D10 4s2. So you can see here all the orbitals are completely filled. See, it is 3D10. It is completely filled. So it is completely filled means it is already in a stable condition. Will it be ready to lose one more of its electron? No, right? So in that case, ionization enthalpy will be higher than what it is expected, right? Yes, so I hope that is clear. So moving on to the next one, the second ionization enthalpy of chromium and copper are unusually high because the electron is now to be removed from the very stable electronic configuration. So what does that mean? From chromium again, we have already written here argon 3d5 4s1. When one electron is lost, that is the first ionization enthalpy is low because it is going to get a half-filled electronic configuration, that is a stable configuration. Now, once it becomes chromium plus, that is argon 3d5. Now it is in a stable electronic configuration. Now second ionization enthalpy means from Cr plus I am going to convert it into Cr2 plus. One more electron I have to remove. That means from the stable electronic configuration I have to remove one more electron. So that will be really difficult, right? No one wants to lose its stability. So if you want to remove one more electron means more ionization enthalpy is required. So the ionization enthalpy is higher than what is expected in this case. So the same goes with copper also. The electronic configuration is argon 3d10 4s1. Okay, so the first ionization enthalpy will be lower than expected. Why? Because if it loses this one electron, it can attain a stable configuration 3d10, right? Completely filled electronic configuration. So now what happens is copper plus one electron, if it is lost, the electronic configuration or it is obtaining a completely filled d orbital 3d10. Now let's come back to the second ionization enthalpy. From the 3d10 I have to remove one more electron. So in that case what happens, the ionization enthalpy will be much higher than expected. Already it is stable, it's not ready to lose its electron. So I hope that is clear. So that is about copper and chromium. The value of second ionization enthalpy of zinc is comparatively low as this involves the removal of an electron, which results in the production of Zn2 plus having stable 3d10 configuration. So we are talking about the second ionization enthalpy of zinc. So we have already written electronic configuration of zinc. First ionization enthalpy means it is getting converted into Zn plus. So Zn plus means what is the electronic configuration? Argon 3d10 4s1. Right. Now that is having a very high ionization enthalpy. That is the first ionization enthalpy. From a completely filled orbital or a stable configuration, we have to remove one electron. So the first ionization enthalpy is really high, but the second ionization enthalpy is comparatively low because we have to remove this one electron. Then again it is going to get a stable electronic configuration 3d10, right? So that is why, because the Zn2 plus, that is the second ionization enthalpy, we are going to get argon 3d10. It's going to get a stable electronic configuration. So what happens in such case, the second ionization enthalpy will be less. Okay. Now the last one, the second ionization enthalpy of manganese is less than that of iron. This is because removal of second electron in manganese produces half-filled d5 configuration. So let's take the electronic configuration of manganese. It is 3d5 4s2. Okay, so first ionization enthalpy means from, this is also a stable electronic configuration, right? It is a half-filled orbital. So what happens? It is difficult to remove the first electron from here. That is Mn plus. It is in argon 3d5 4s1. But the second ionization enthalpy will be low. Why? Because it is easy to remove this electron. Once this electron is removed, it is going to attain a half-filled electronic configuration. So I hope that is clear. So these are the examples that we have discussed in detail. I hope it is clear. So this is about the trend in ionization enthalpy. So the answer for all this ionization enthalpy related, which is linked to the ionic radii or atomic radii, it comes with the electronic configuration of this atoms itself. So once you are clear with the electronic configuration, you will get to know why it is low or why it is high. It is because that it is going to either attain a stable configuration, or it is not ready to lose its stability and lose one electron. So all the answers lies in the electronic configuration itself. So once you are clear with that, the concept will be also clear for you. So in the next session, we are going to study about oxidation states. So I hope the concepts that we have cleared in this session is clear for you. So that's all for today. Thank you.